In this video, we'll be discussing acids, bases, and salts. So let's go ahead and start with acids. Now, acids produce hydrogen ions in aqueous solution. Now, sometimes acids can also be defined as proton donors. They are proton donors in the sense that they can donate this hydrogen proton to some other substances. For example, when acids react with bases, they donate these protons to bases. So then this means that when I'm talking about acids, acids have the hydrogen ions with them. So you can have examples like hydrochloric acid. Notice that it has H, and you can talk about sulfuric acid, and it also has hydrogen ions. Or you can talk about nitric acid with an H there. So these substances called acids, because of the hydrogen with them, usually when they are in aqueous solution, they try to produce these hydrogen ions or perhaps donate them to some other substances. Now, there are two types of acids that you need to be familiar with. There is what we call strong acids and also weak acids. When you're talking about strong acids, these acids ionize completely in aqueous solution. What it means is that when you remember the definition of acids, let's say that this is an acid. So when this acid is placed in aqueous solution, you're going to see that it is going to produce the hydrogen ions, and then it is going to remain with the other conjugate base. Now, in this case, when you look at the reactant that you have, the main reactant there, if you see that all the protons have completely separated from the acid, then that means that this is a strong acid. However, when you have something like, if you have, let's just say H2, and then this is substance X, and then this is going to give us H plus, and let's say you have HX like this. Because you have remained with some hydrogen with the main substance that you have, then this means that this is partial ionization because some hydrogen have remained here. So when an acid completely ionizes in aqueous solution, then that is a strong acid. Whereas if it partially ionizes in the aqueous solution, then that is a weak acid. So for weak acids, they ionize partially in aqueous solution. So make sure that you understand the differences between weak acids and strong acids. So what are some of the examples of weak acids and strong acids? For strong acids, you have hydrochloric acid. This is a strong acid, which means that it ionizes completely in aqueous solution. You can talk about nitric acid. You can also talk about sulfuric acid. These are the main examples of strong acids. Now, when you're talking about weak acids, for the most part, you have what we call carbonic acid. You can have ethanoic acid. And these are some of the examples, because when you try to put these acids in aqueous solution, you see that because they seem to have more than one hydrogen atom, then usually when they try to dissolve, they only ionize partially. Whereas when it comes to sulfuric acid, for it ionizes completely when it is in aqueous solution. So just make sure that you understand the examples and the differences between the two types of acids. Now, what are some of the general properties of acids? Well, the first thing is you realize that acids have a sour taste. Not only that, these acids usually turn blue litmus paper red. So they turn blue litmus paper red. So this is one of the key properties of acids. When you try to pour acids on blue litmus paper, you see that it's gonna turn red. Now, acids also conduct electricity in solution. So they conduct electricity in solution. They also react with bases. So they react with bases usually to form salt and water. And another key property of acids is that their pH is actually less than 7. So the pH is less than 7. And keep in mind, for most of these properties, when you come to discuss the bases, they usually have the opposite of this. So if you understand this, it is going to help you distinguish between acids and bases. Now, when you look at acids like hydrochloric acid and nitric acid, you see that these acids are actually called monoprotic acids. This means that they only release one hydrogen ion when in aqueous solution. And it makes sense because when you look at this, they only have one hydrogen ion. So because they release only one hydrogen ion, they are actually called monoprotic acids. So mono means one. Now for acids like sulfuric acid, when you look at it, you see that this is not a monoprotic acid. Instead, this is called a diprotic acid. So di means two, and when you look at these two hydrogen atoms there, you can clearly see that when sulfuric acid dissolves in aqueous solution, it is going to produce two hydrogen ions. So that's why it's called a diprotic acid. So make sure that you understand these concepts. Now, the other important point also to note here is that when you're talking about strong acids, strong isn't equal to concentrated. When you have concentrated acid, that is quite different from strong acids. Similarly, when you are talking about weak acids, that is not equivalent to dilute acid. Because when you're talking about strong acid, you're talking about complete ionization rather than concentration. And when you're talking about weak acids, you're talking about partial ionization instead of dilution. So make sure that you understand these concepts. So here's the question for you. Which acid ionizes completely in water? So A, you have ethanoic acid. Is it the answer? B is carbonic acid. And C is hydrochloric acid. And lastly, you have ammonium hydroxide. So which one do you think is the correct answer? Well, the first choice is actually ethanoic acid. Now, this is probably a weak acid, so it cannot ionize completely in aqueous solution. Notice also that you have many hydrogen atoms in it, so this cannot be the answer. Now, the same is true for carbonic acid because this falls under the weak acids. Now, this is obviously excluded, and you notice that hydrochloric acid is the best choice for this particular question because it falls under strong acids which ionizes completely in aqueous solutions. So make sure that you understand that when you're talking about weak acids, they partially ionize in aqueous solution. And you have to know how to define strong acids and weak acids and also be able to give examples of each. Now, the next thing that we're going to look at is the reactions of acids. And the first thing is for us to understand that acids usually react with metals. Now, this means that when you have a metal and you react it with an acid, this is going to give you salt and hydrogen. So an example of this will be a metal, let's say this is zinc, and zinc reacts with sulfuric acid. And when it does so, you're going to get a salt here, which is zinc sulfate, and then plus hydrogen gas. So make sure that you understand, because in this case, a metal, when it reacts with acids, it is going to basically displace hydrogen from its acid, and then this same metal is going to replace hydrogen, and then you're going to have hydrogen gas like that. So this is more like a displacement reaction. A metal displaces hydrogen from its acid, and then that metal replaces hydrogen, and then you have hydrogen and a salt like that. Next, acids usually react with bases. Now, when you react an acid plus a base, this is going to give you salt and water. So an example of this would be, let's say hydrochloric acid reacts with sodium hydroxide, and this is going to give us salt, which will be sodium chloride here. So we're going to have sodium chloride plus water, which is H2O. So in this particular case, you see that this is more like a double displacement reaction. So hydrogen is going to replace this metal, which is sodium, and sodium is going to react with chloride here. When you get something like that, the result is sodium chloride and water. So make sure that you understand how these reactions take place. Now, acids can also react with carbonates. So you have an acid plus carbonate, and that is going to give you salt plus water plus carbon dioxide. So notice that these reactions are different. And an example of this will be, let's say we have hydrochloric acid as our acid, and then the carbonate will be calcium carbonate. And when these react, we are going to get calcium chloride plus water plus carbon dioxide. So make sure that you understand how these reactions take place, especially when acids react with metals or with bases or with carbonates. For carbonates, you have to understand that carbon dioxide is going to be produced, water is also going to be produced, plus a salt. And that salt, of course, is when a metal in a carbonate reacts with, let's say, chloride ions or maybe sulfate ions in the case of sulfuric acid or some other ions. So make sure that you understand this. Now, acids can also react with metal oxides. So this means that when you react an acid plus a metal oxide, you're going to get salt and water. So an example of this would be, let's say an acid will be, let's just use hydrochloric acid again, and then we are going to use copper oxide as our metal oxide. Because remember, metal oxides are metals after they react with oxygen. So they form what we call metal oxides. So in this case, copper reacted with oxygen to produce copper oxide. So when hydrochloric acid reacts with copper oxide, what are we going to get here? Notice that we have to get salt and water. So in this case, salt will be copper reacting with chloride ions. So we're going to get copper chloride. And we are also going to get water here. So make sure that you know how these reactions are taking place. Now, the next thing that we want to talk about is actually bases and alkalis. So how can you define a base? Now, a base is usually the opposite of an acid. Bases produce hydroxide ions in aqueous solution. And bases are also proton acceptors. Because for the most part, bases react with acids. So while acids produce protons like hydrogen ions, they're also called proton donors. So when they donate those hydrogen ions, usually bases accept those hydrogen ions. That's why they're also called proton acceptors. Now, make sure that you understand that instead of producing hydrogen ions, bases produce hydroxide ions in aqueous solutions. Now, keep in mind, if bases produce hydroxide ions, then they should possess hydroxide ions in their structure. So make sure that you recall that just like acids should possess hydrogen in their own structure for them to produce hydrogen ions in aqueous solution, the same is true for bases, except that for bases they are producing hydroxide ions. Now, when you're comparing alkalis with bases, you realize that all alkalis are bases, but not all bases are alkalis. So what does that actually mean? Now remember that bases usually produce hydroxide ions when in aqueous solution. So any base that dissolves in aqueous solution to produce hydroxide ions is actually an alkali. But some bases might not necessarily dissolve in aqueous solution. So those bases, though they are bases, but they are not alkalis. The same is true for bases like ammonia. Ammonia is a base, but it doesn't really produce hydroxide ions on its own just like that, unless it dissolves in water. So ammonia is a base, but it's not an alkali. Likewise, other bases that cannot dissolve in aqueous solution, they are bases, but they are not alkalis. So all alkalis are bases, but not all bases like ammonia or some bases that might not dissolve in aqueous solution are actually alkalis. So make sure that you understand the differences here. So when you're talking about alkalis, examples would be sodium hydroxide. The other will be potassium hydroxide. And the other one would be calcium hydroxide. And even ammonium hydroxide. All these are alkalis, but you have some insoluble bases like, let's say, copper oxide is an insoluble base, and you have iron hydroxide, and so on. So make sure that you understand the differences between alkalis and bases. Now, what are the general properties of bases? While acids have a sour taste, bases are actually bitter. They have a bitter taste. Not only that, they are soapy. And when it comes to litmus paper, they actually turn red litmus blue. So as opposed to acids which turn blue litmus paper red, bases usually turn red litmus paper blue. So make sure that you understand that. And when you're talking about the pH of bases is actually greater than 7. So for acids, less than 7. For bases, greater than 7. And 7 itself is a neutral pH on which solutions like water fall under. So keep in mind, these are some of the general properties of bases which you want to be familiar with. So as you can see, it's very important to actually distinguish between alkalis and bases, because you might be tested also on that. You might be asked to define an alkali or simply differentiate between a base and an alkali, or maybe they can ask you to state which statement is true. For example, which statement is true, and then you have options like all bases are alkalis, which is wrong, or all alkalis are bases, which is right. So you have to make sure that you understand all those principles. Now, the other thing that we can talk about is indicators. Indicators, when you're talking about indicators, these are trying to show you whether the solution is acidic or alkaline. So you might have a solution and then you want to know whether it is an acid or a base. What are some of the indicators? So that's the purpose of discussing indicators. And when you're talking about indicators, the common indicators that we can talk about are, let's say, blue litmus. When you're talking about blue litmus and you have a solution, you can dip that blue litmus into the solution, and if the acid is present, then you see that an acid turns blue litmus paper red. So that's quite important for you to understand. Now, if the indicator is actually red litmus, then in this case you realize that if a solution is a base, then it's going to turn this red litmus into blue. Now, the other indicator that we can talk about is actually phenolphthalein. Now, how does phenolphthalein work? Well, if you use phenolphthalein, if an acid is present, it is going to turn this indicator colorless. Whereas if the base is actually present, then the base is going to change this indicator to pink. So if you have a solution and this indicator phenolphthalein, then try to dip this indicator, mix an acid with phenolphthalein, and then you're going to see that if it's an acid, it's going to turn this phenolphthalein into a colorless solution, or if it is a base, then it's going to turn this indicator into pink. So make sure that you understand this. Now you can also have what we call methyl orange. Now for methyl orange, if an acid is present, then it's gonna turn this methyl orange to red. Whereas if an alkali is present, then it's gonna turn this methyl orange to yellow. So make sure you get the concepts of these indicators, because you might be tested on this as well. Now, we also have what we call the universal indicator. Now, the universal indicator actually shows pH colors. So it shows pH colors. So that's why it's called universal, because it is trying to show a range of colors on the pH. When you look at the pH scale from 0 to 14, the universal indicator is able to show all the possible colors within the pH scale. Here's a question for you. Phenolphthalein in acid turns A pink, B blue, C colorless, and D yellow. What would you say? Well, all you have to do is recall that if it is an acid, then this phenolphthalein is going to change into colorless. But if it is a base, then pink would be the best solution if it is a base. But in this case, because it is an acid, then obviously the correct answer for us is actually C. And you might be asked, like, which indicator. You might be given a list of indicators, and then they say which indicator gives pH range, or it gives different ranges of pH. You know that it is a universal indicator that does so. So make sure that you understand these concepts. Now the next thing that we can talk about is the pH scale. When you are talking about pH, you have something like this. So you have, let's say this is 7, and you're going to have 0, and here you're going to have 14. So here you're going to have 8, 9, 10, 11, 12, 13. So let's do this. And here you're going to have 1, 2, 3, 4, 5, 6. And what you realize is that here you have neutral, but then this is going to be the bases, and this is going to be acids. So below 7 you have acids, so that is the acidic pH less than 7, and above 7 you have the alkaline pH. In fact, we can write alkaline here, or alkalis. So this is acidic in this region, and then this is alkaline in that particular region. So make sure you understand that when the pH is less than 7, then it is acidic. Whereas when the pH is greater than 7, then it is alkaline. And the neutral is actually 7. So make sure that you understand these principles. And each pH is something that changes by 1 unity, because you're just moving from 1, 2, 3. So the change is just by 1 unity. Those are some of the things that you want to be familiar with. The next thing we want to talk about is neutralization. When you are talking about neutralization reactions, what you are talking about is you are trying to make something neutral. So, for example, you have acids whose pH is less than 7, and you have bases whose pH is actually greater than 7. Neutralization is about combining the two so that you have a neutral pH. Notice the word neutral. Neutralization simply means that you're trying to make a solution neutral. By reacting two solutions, you get something that is neutral. So that is what we mean when we say neutralization reactions. So this means that when you're talking about neutralization reactions, the general equation would be acid plus base is going to give us salt plus water. This is a neutralization reaction. Make sure that you understand that. So let's say an acid will be sulfuric acid, and a base in this case would be, let's say, sodium hydroxide. And so we are going to get sodium sulfate as our salt plus water. Now this is not balanced. If you want to balance this, make sure that you balance it. You have 2 sodium atoms here, so you can put a 2 here, which means that you have 4 hydrogen atoms on the left side. You need 4 more here, so you put a 2 here. So this is an example of a neutralization reaction. Make sure that you get the concept of this. And when you're talking about neutralization reactions, they have interesting applications as well, because it is of great use in agriculture, in industries, and even in medicines. When you're trying to make chemical drugs, you want to make sure that they fit the range of blood pH, which is 7.35 to 7.45. So we want to make sure that any drug or medication is actually neutral. So you use neutralization reaction to make sure that it fits this particular pH. So when you're talking about neutralization reaction, you only have 2 products. You have salt and water only. These are the only products you're going to get when you're dealing with neutralization reactions. So make sure that you understand these concepts. Now, the next thing that we want to talk about is salts. So what are salts? Well, when you're talking about salts, salts are compounds formed when hydrogen ions of an acid are partially or completely replaced by metal ions or ammonium ions. So let's make sure that we write that these are compounds formed when hydrogen ions of an acid are partially or completely replaced by metal ions or ammonium ions. So make sure that you understand the key points here. The hydrogen ions of an acid, like hydrochloric acid, they are partially or completely replaced by what? Metal ions, or in some cases, ammonium ions. So how can we understand that? Well, it's quite simple. All you have to do is to go back to the neutralization reaction. Let's say that we have hydrochloric acid reacting with sodium hydroxide, and this is a neutralization reaction giving us sodium chloride plus water. So notice what is happening here. What happens is that you have an acid with this hydrogen ion. So what happens is that when this hydrogen ion is completely replaced by a metal or partially, then the new substance is what we call a salt. So a salt is a substance formed when this hydrogen in an acid is partially or completely replaced by sodium or a metal ion like sodium. So it replaces hydrogen and then it becomes sodium chloride, while you have another product here which is water. So make sure you understand that. Now there are different types of salts. The first one is what we call the normal salts. What do you think are the normal salts? Now, when all hydrogen ions are replaced in an acid, we get what we call normal salts. All hydrogen ions are replaced. So, for example, when you get sodium chloride, notice that you can't see any hydrogen ions in this particular salt. So that is because this sodium metal completely replaced the hydrogen in the initial acid, which was probably hydrochloric acid. So because the fact that you can't see any hydrogen ions in this particular salt shows that this metal completely replaced the hydrogen ions. And so that type of a salt is actually called a normal salt. The same is true for salts like potassium sulfate. You can't see any hydrogen ion in this particular salt, which means that this is also a normal salt. So it's quite easy to understand, not so? Now, the second type is what we call the acidic salts, or the acid salts. Now, what are acidic salts or acid salts? Well, this simply means that even though you have formed some salt, they still have some acidic properties, and that can only be possible if only some of the hydrogen ions have been replaced. So the hydrogen ions are partially replaced in that particular case. We can give some examples. Let's say sodium hydrogen sulfate. This is a salt, but it is an acidic salt in the sense that it still has the hydroxide ion in itself. Or maybe we can say sodium hydrogen carbonate. Sodium hydrogen carbonate is also another example of an acidic salt because you still have some hydrogen there which remain, making it still possess some acidic properties. Now the third type is what we call the basic salts. Now the reason why they are called basic salts is because they contain some basic properties. In other words, they contain hydroxide ions. Now an example of this would be, let's say, magnesium chlorohydroxide. So this is magnesium chlorohydroxide, because it contains some hydroxide ions, it is still a salt, but this is a basic salt, meaning it possesses some basic properties. Now the other type will be what we call the double salts. What are double salts? Well, double salts usually contain two cations. They contain two cations. What does that mean? Well, you might have something like this is called potash alum. This is just an example of a salt that contains two cations at the same time. And the reason is because you have two metals here which are good producers of actually the same cations. So you just have to get the concept of what double salts are and you are good to go. Now sometimes you might also have what we call the complex salts, but I think you just have to know them like that. I don't think you will be tested on that during O-level chemistry exam. But the other two key types of salts that you wanna be familiar with are called hydrated salts. Now, hydrated salts usually contain water molecules. Notice the word that it is hydrated. So these types of salts contain water molecules. So you might have something like hydrated copper sulfate solution. So you have copper sulfate, and then this is going to be 2HO. So this is an example of anhydrated salt. So it is the same salt, it's copper sulfate, but this is hydrated, which means that it contains also the water molecules. Now the opposite of that is actually what we call anhydrous salts. Now anhydrous salts do not contain water molecules. So an example of this would be just the same hydrated salts. The opposite of that, when you remove all water molecules, you remain with copper sulfate. So this is anhydrous salt. So sometimes you might be tested on this where you are given options and then they ask you to identify the salt that contains water molecules. Make sure that you see that any salt containing water molecules is actually anhydrated salt. So make sure that you understand. The next thing that we want to talk about is how to prepare soluble salts. So soluble salts mean that these are the salts that can dissolve in water or in any solvent. So how do we prepare soluble salts? Well, the first method, which we'll call method 1, would be usually through titration. So this is the situation where we react an acid plus an alkali, and then we get salt and water. Salt and water. So notice that we are using alkalis, which means that this is a soluble solution. And when we have something like this, then the salt that we are going to get is probably going to be a soluble salt as well. So let's give some examples of this. So let's say we have hydrochloric acid plus sodium hydroxide, which is an alkali, and we're going to get sodium chloride plus water. So this sodium chloride salt is a soluble salt. This is one of the methods we can use to prepare soluble salts, just using titration. Now, method 2 would be reacting an acid with a metal. So an acid plus a metal is going to give us salt plus hydrogen. Now, this means that if we try to use some examples here, again, zinc, when it reacts with sulfuric acid, is going to give us zinc sulfate plus hydrogen. So in this case, zinc sulfate is also a soluble salt. Now you can also look at method 3, where you react an acid with a carbonate, as we've looked at before, and then this is going to give you salt plus water plus carbon dioxide. So again, you're going to have calcium carbonate plus hydrochloric acid. This is going to give you calcium chloride plus water plus carbon dioxide. So this calcium chloride again is a soluble salt. That's another method you can use. Now, you can also react an acid with an insoluble base. So let's say this acid is going to be sulfuric acid plus an insoluble base will be copper oxide. So this is going to give you copper sulfate plus water. So in this case, again, this copper sulfate is going to be a soluble salt. So make sure that you understand. But usually this type of a salt, it is collected in form of crystals. And the steps for this particular reaction will be that when you put an acid in a certain reacting chamber, you add excess reactant. In this case, you have copper oxide, and then after the reaction, you are going to filter the excess, and then you evaporate. After you've evaporated, you are going to cool the remaining substances that you have, and then when you cool, you're going to collect these crystals. But for the most part, these crystals are still going to be soluble. So that's how you collect or get copper sulfate crystals like that. And keep in mind, when you're trying to prepare soluble salts, usually you use titration, because you might be tested also on that one, where you are asked to find the proper method to use when preparing soluble salts. Titration is the best method to go for. And in this case, where you are trying to prepare copper sulfate crystals, the reason why you have to add the excess of this insoluble base is to make sure that all the acid reacts. Here's a question for you. Describe the preparation of zinc sulfate crystals from zinc metal. How would you describe that one? Well, the first thing to notice here is that you are preparing zinc sulfate. So because you have sulfate here, then obviously the type of an acid that you're going to use is sulfuric acid, because sulfuric acid is going to donate this sulfate to you. And you're going to react that sulfuric acid with zinc, because you've been told here that you're going to prepare these crystals from zinc metal. So these are the two reactants that you're going to have. So the first thing is you're going to add excess zinc metal to dilute sulfuric acid. So when you do that, what reaction are you going to get? Now, remember that when you're reacting this zinc metal with sulfuric acid, you have to get zinc sulfate. And in this case, it's quite easy to get zinc sulfate because this zinc is going to displace hydrogen from its compound, and you're going to have zinc sulfate, and that hydrogen is going to be on its own like that as hydrogen gas. And as you can see, this equation is actually balanced. If it is not balanced, please make sure you balance that equation. So this will be the second step, and the third step is going to be to filter. Make sure you filter the excess zinc. This is to make sure that you remain with a clear solution. And after you've filtered like that, the next step is evaporate the filtrate that you have. And after that, you can cool the crystals. So those crystals are zinc sulfate crystals. So always add excess metal because you want to make sure that all the acid reacts, so that what remains there, the zinc particles, are going to be filtered out. So make sure you understand these principles on the preparation of soluble salts. The next thing we want to talk about is the preparation of insoluble salts. So how do you prepare the insoluble salts? Well, the first method is what we call the precipitation. Now, when you're talking about precipitation, usually you're trying to use two soluble solutions. And they are going to give you an insoluble precipitate. So an example of this will be reacting barium chloride with, let's say, sodium sulfate. And these are in aqueous solution. And what you're going to get is barium sulfate, which is an insoluble salt, plus sodium chloride. So here you are going to have a 2 to make sure that the equation is balanced. So keep in mind, when you look at this, you are using two soluble solutions. In this case, barium chloride and sodium sulfate. And pay attention to the state symbols here. It is in aqueous solution or aqueous state, aqueous state. When you use two soluble solutions, you get an insoluble salt, and the state symbol here is actually solid. But for sodium, this is actually an aqueous solution because it is insoluble. So as you can see, it's not really difficult as well to prepare insoluble salts from two soluble solutions using precipitation method. Now, the steps for this precipitation method are quite simple. First, you mix the two solutions. Next, after they have reacted, you are simply going to filter the precipitate. Then after you filtered, then you can wash the precipitate, and then finally you can dry the precipitate to get an insoluble salt. So as you can see, it's not really difficult to actually know how to prepare insoluble salts using precipitation method, because keep in mind you're just using two soluble solutions, and that is going to give you an insoluble salt or an insoluble precipitate. So just like when you're dealing with soluble salts, you might be asked which is the best method you can use to prepare soluble salts. You know that it's titration. For insoluble salts, you might be asked the same question. You use precipitation. This is the method you use to prepare insoluble salts. So make sure that you understand. Here's a question for you. Describe how you can prepare silver chloride. Now, silver chloride is an insoluble salt. So how do you prepare silver chloride? Well, the fact that you have chloride here, this simply shows that you want to use a chloride substance. In this case, usually when we are preparing silver chloride, we use sodium chloride. So sodium chloride will be one of our reactants. And the other one, which should contain silver, usually we use what we call silver nitrate. So these are the two soluble solutions that we are going to use to prepare an insoluble salt of silver chloride. So let's go ahead and write a balanced chemical equation for the reaction. So we are going to have silver nitrate, which is in aqueous solution, plus sodium chloride, which is also in aqueous solution, and this is going to give us silver chloride. So silver chloride will be like this, and this is in solid state, plus sodium nitrate. So this is going to be in aqueous solution. So basically, this is how you get silver chloride. Following the same steps, you make sure that you mix the two, that is mixing silver nitrate and sodium chloride together. And when you see that this precipitate has been formed, then you filter this precipitate and you wash it thoroughly, you dry it, and then you have what you need. So two solutions produce an insoluble salt. Usually when they ask you to state the name of this particular reaction, it is called precipitation reaction. But it is also called double decomposition reaction, because as you can see, there should be the decomposition of both silver nitrate and sodium chloride so that these can mix together to have everything that you have on this side of the equation. So make sure that you understand these principles because they are very important. Now, when preparing barium sulfate, an insoluble salt, sometimes you can also use barium nitrate, and this is in aqueous solution, and then you react it with magnesium sulfate, which is also in aqueous solution, because all these are soluble solutions, and you're going to get barium sulfate, which is an insoluble salt, plus magnesium nitrate, which is going to be in aqueous solution. So this is also one method you can use to prepare barium sulfate, but it is a precipitation reaction or a double decomposition reaction. So make sure you get the concept, because whenever you're asked about finding how to prepare an insoluble salt, you use precipitation by reacting two soluble solutions together, and then they are going to give you an insoluble salt plus another solution based on that double decomposition reaction. Now the next thing that we want to talk about is solubility rules. How do you know that this salt is insoluble, this salt is soluble? So that's what this is all about. Now there are some rules that we need to follow. And the first rule is going to be that these salts are always soluble. So what are these salts? Well, all sodium salts are soluble. So you can talk about sodium chloride, you can talk about sodium sulfate, and so on. These salts are always soluble. As long as these are sodium salts, then they are obviously soluble. Now, the other thing is that the same is true for potassium salts. So you can talk about potassium sulfate and so on. And the other thing is even ammonium salts are also soluble. So you can talk about ammonium nitrate. And the other thing is that all nitrates are soluble. All of them. If you just see that the salts that you are dealing with are nitrates, then all of them are soluble. So make sure you understand these principles because they can help you identify soluble salts, like these salts which are always soluble. Now the following types of salts are soluble except some. So let's say these are soluble. So we'll say chlorides are soluble except, so we are going to have exceptions. So silver chloride is insoluble, and lead chloride also is insoluble. So all chlorides are soluble except silver chloride and lead chloride. And usually when you see silver chloride or lead chloride, even though these are chlorides, they are actually insoluble. Now the other type would be sulfates. All sulfates are actually soluble with the exception of, so we'll have something like barium sulfate, and the other one will be lead sulfate, and the other one will be calcium sulfate. These are insoluble, but all other sulfates are actually soluble. Now, some are insoluble for example, these carbonates are actually insoluble except, so you have sodium carbonate, and we can have potassium carbonate as well, and even ammonium carbonate. All these salts are actually soluble. So they are soluble, but all other carbonates are actually insoluble. So with the exception of these three, for the most part, all other carbonates are actually insoluble. Now, the same is true for hydroxides. All hydroxides are actually insoluble with the exception of sodium hydroxide and potassium hydroxide for the most part. So sodium hydroxide and potassium hydroxide are actually soluble, or even calcium hydroxide. So calcium hydroxide is also soluble, but all other types of hydroxides, they are actually insoluble. So keep in mind, nitrates are soluble. All nitrates are soluble. And when you're talking about other salts that are always soluble, usually for the most part, sodium, potassium, and ammonium salts are always soluble. So here's a question for you. Which sulfate or salt is insoluble among the 4 options here? What would you say? Now, remember that all the sodium salts, potassium salts, and ammonium salts are soluble. Just make sure you understand that any type of salt that you see, and it is a sodium, potassium, or ammonium salt, just know that it is soluble. So you can clearly see that this is the correct answer. Barium sulfate is an insoluble salt here. And this is very important because it will help you know how to even deal with precipitation reactions, because you will know that, okay, if I react this soluble solution and this soluble solution and they give me an insoluble salt, you can confirm just by looking at the type of a salt that you get that this is an insoluble salt by looking at the solubility rules. So make sure you understand these rules because they are very important. Now the next thing that we are going to look at is actually oxides. So when you're talking about oxides, you're talking about substances that have oxygen. For example, copper oxide is an oxide because it has oxygen. You can talk about even sulfur trioxide. This is an oxide also because it contains oxygen. Carbon dioxide is an oxide also because it contains oxygen. So these are some of the examples of oxides. But oxides can actually be of different types. So the first type that we can look at is acidic oxides. Now, these oxides usually react with water to form acids. So that's why they are called acidic oxides, because they produce acids. So for example, we can say sulfur dioxide can react with water to produce sulfurous acid, which is H2SO3. So this is an acid, though it is a weak acid, but it is indeed an acid. Now the other type would be the basic oxides. So these basic oxides react with water to form bases. So an example would be, let's say, sodium oxide plus water. This is going to give us sodium hydroxide. So we can balance this by putting a 2 here. But as you can see, when you react this sodium oxide with water, it's not giving us an acid, rather it is giving us a base. This implies that this basic oxide is indeed basic because it is producing a basic compound. So you see that in this case, even calcium oxide will be in the same category, or even magnesium oxide is also going to fall into the same category. Now, the other type of oxides that we can look at would be what we call the amphoteric oxides. Now, amphoteric oxides react with both acids and bases. Now, what they do is that when they react with acids, they act like bases. And when they react with bases, they act like acids. And the key examples of amphoteric oxides would be zinc oxide and aluminium oxide. So these are the key examples of amphoteric oxides. So zinc oxide can react with hydrochloric acid, and this is going to give us zinc chloride and water. So to make sure that you balance the equation, there are 2 chlorine atoms here and 2 hydrogen atoms. So we can simply put a 2 here and the equation is balanced. Now we also have what we call neutral oxides. Now for the most part, these neutral oxides do not react. These would be oxides like carbon monoxide or nitrogen monoxide. So when you have something like this, these types of oxides for the most part do not react. And those are some of the examples that we can give for these particular types of oxides. So as you can see, this is also an important information, because you can see an oxide reacting with an acid, and then you see that, okay, this is an oxide participating in a neutralization reaction. And sometimes you might be asked to identify which one of the following oxides. And sometimes you might be asked to identify an amphoteric oxide, for example, from a list of oxides that you've been given. For example, you can have carbon dioxide, and you can have magnesium oxide, and you can have, let's say, zinc oxide, and you can have sulfur dioxide. So which one is an amphoteric oxide? Well, you can clearly see that zinc oxide is an amphoteric oxide. Or if you don't have zinc oxide, you might have aluminium oxide. You want to go for that one because it is an example of amphoteric oxides. Now the same is true for neutral oxides. They might ask you to identify a neutral oxide. So make sure that you absorb this information because it's very, very important. Now, what are some of the applications of salts? Well, the first thing, or the first application that we can talk about is, we can say, food preservation. Now, why is that important? Well, sometimes you use sodium chloride to preserve food from undergoing decomposition so easily. So if you haven't put salt in your food, usually it's not going to last for a long period of time. Usually, even when you catch fish, you apply salt because you know that salt is going to preserve your food. And also cooking would be one of the applications of salts. Now, the other thing is salts like calcium carbonate can be used in cement production or even limestone. So in industries, you use calcium carbonate in different things. And calcium carbonate, notice that it is a carbonate salt. And so it is very, very important to have salts like calcium carbonate. And also the other thing is when you're talking about, let's say, potassium nitrate. Potassium nitrate is usually used in fertilizers. So that is also another important application of salts. So as you can see, sometimes you might be asked to identify the common salt that is used for food preservation. And you know that that is clearly sodium chloride, or the salt that is used in fertilizers, you know that is calcium nitrate, or the type of salt that is used in cement production, you know that it's calcium carbonate. So these are quite important points that you want to be familiar with. Now, the next thing that we want to talk about is qualitative analysis. And under this particular theme, what we want to discover is we want to know how to identify the aqueous cations. So let's say we want to understand the identification of aqueous cations or cations. So we want to understand the identification of these aqueous cations using characteristic reactions. So here's what we are going to do. There are common cation tests that we have in chemistry. And so let's go ahead and look at them. So we have common cation tests. And remember that the cations are positively charged ions like sodium ion or copper 2 ion. These are cations. They are positively charged ions. So the first one will be the copper 2 ions. How do you identify the presence of copper 2 ions? Now, all you have to do is add sodium hydroxide to any solution containing copper 2 ions, and this is in aqueous solution. And what you're going to observe is that you have a blue precipitate that is going to be formed. Now, that blue precipitate is as a result of what we call copper hydroxide, because when you react these copper ions with sodium hydroxide, notice that copper is going to react with hydroxide. And so when you have something like copper 2 ions and then plus, this is going to be our hydroxide ions, this is going to give you something like copper hydroxide. And this copper hydroxide is actually a blue precipitate. So make sure you understand that, because it is showing you that when you add sodium hydroxide or any other hydroxide to a solution containing copper 2 ions, you have a blue precipitate. So when you see a blue precipitate, just know that copper hydroxide has been produced, and therefore that is a sign that copper 2 ions are present. Now the next example of ions is actually iron 2 ions. So even in this case, add the same solution, which is sodium hydroxide, and when you do this, you're going to observe a green precipitate. Now, why is that? Well, again, it's because the iron 2 ions are going to react with the hydroxide part here. So you're going to have iron 2 ions, which is going to react with the hydroxide ions, and these are going to give you iron hydroxide. And this iron hydroxide is actually a green precipitate. Now, when this green precipitate is left like that on standing, it may turn to brown. So this can actually turn to brown. So make sure you understand these principles. So because of iron hydroxide which is produced, you have a green precipitate, and on standing, that green precipitate may actually be turned to a brown precipitate. Now the third cation that we can look at is actually iron 3 ion. Now you do the same thing, you add sodium hydroxide, And what you are going to see is that you're going to observe a brown precipitate. Now, why is that? Well, again, it is because this ion 3 is reacting with sodium hydroxide, and this is giving you iron hydroxide. So this is a brown precipitate, and when you use iron 2 ions, you're going to see that you get a green precipitate. But the reason why that green precipitate can turn to a brown precipitate on standing, it is because it goes further to produce this particular compound, which is brownish in color. So make sure you understand these principles. Now, the next cation is zinc. So again, you add sodium hydroxide. What are you going to get? Well, in this case, you are going to get a white precipitate. Now, why is that? Again, the reason is zinc 2 ions react with hydroxide ions, and the result you're going to have is zinc hydroxide. Now, this zinc hydroxide is actually whitish in color, so that's how you get this white precipitate. Now, the fifth cation that we can look at is actually ammonium ions. So, as usual, you add sodium hydroxide, but this time you also add some heat. Now, the reason why you want to add some heat here is because not only are you trying to increase the rate of chemical reaction, but also there's a gas that is produced during this reaction, and the heat applied quickly helps to release this gas and make the smell obvious. Because when you are trying to identify the presence of ammonium ions, what you're going to see is that you're going to see ammonia gas released. So it's going to be released, and when it is released, because it is basic in nature, it is going to turn litmus paper blue. And the reason why you have ammonia in this case is because when ammonium ions react with hydroxide ions, you're going to have ammonia plus water itself. So this is what you're going to have. And so this is how you test for ammonium cations. Now, sometimes you might also be required to know the flame tests. In other words, when sodium ions are present, then under heat, you're going to see that it produces a yellow flame. For potassium ions, you're going to see that lilac flames are produced. And for calcium ions, you see that it is brick red. And if you are talking about copper 2 ions, then for these, what you're going to observe is blue, green. These are some of the colors that you can notice from these flame tests. So make sure you understand these principles. Here's a question for you. A blue precipitate with sodium hydroxide suggests A, iron 3 plus ions, or copper 2 plus ions, or zinc 2 plus ions, or ammonium ions. What would you say? Well, if you remember, this produces a brown precipitate. If it is iron 2, then you are going to have a green precipitate. Now, copper produces a blue precipitate. And zinc, if you remember, produces a white precipitate. And for ammonium, you have ammonia gas. So as you can see, B is the correct choice in this particular case. Now, we can also look at the identification of anions or anions. And these are negatively charged ions like oxygen ion, or you can have sulfate ions, and so on. So these are some of the examples of anions. These are negatively charged ions. So how can you identify these? Well, we'll first look at the common anions. And the first one will be the carbonate ions. So how do you identify the carbonate anions? Well, the first thing that you have to do is you have to add an acid. And when you add an acid, notice that because of the carbonate ions here, probably you are going to get carbon dioxide. And so for that reason, you're going to see some bubbles indicating the presence of carbon dioxide. Now, when this carbon dioxide passes through lime water, this lime water actually turns milky. So as you can see, it's quite easy to understand or identify the presence of the carbonate ions, because most likely you know that carbon dioxide is going to be produced, and when it is produced, you are going to see some bubbles showing the presence of carbon dioxide, and when that is passed through lime water, this lime water is going to turn milky, and so that shows the presence of carbonate ions in any particular solution. Now, the next type of anion would be the sulfate ions. The thing that you want to do here is that you want to add barium chloride solution. Now, the reason for that is when you add barium chloride, there is an insoluble salt that you're going to get, and that is barium sulfate. And because of the presence of that barium sulfate, you're going to see actually a white precipitate. And that white precipitate is actually barium sulfate. So as you can see, this is quite easy. So barium sulfate is the product you're going to get. So if you want to know the presence of sulfate ions here, just add barium chloride solution, and the reaction will take place where barium sulfate is going to be produced, and this is a white precipitate. Now the third one will be the chloride ions. Now for these chloride ions, again, you can add silver nitrate solution. And the reason for that is because you want to make sure that this silver is going to react with chlorine ions to produce, again, another white precipitate, which is silver chloride. So when you add the two, you're going to get another white precipitate. This white precipitate is actually silver chloride. Here are some questions for you. Question 1. Which ion gives white precipitate with silver nitrate? Well, because of silver here, you know that you're going to get silver chloride. So this is probably the ion that is going to give a white precipitate with silver nitrate. If you want to react that silver nitrate with any of these other ions, A, B, or D, chances are that you're not going to get the white precipitate. So C is our answer. Question 2. Carbonates produce, is it hydrogen, oxygen, carbon dioxide, or ammonia? Well, the name itself, carbonates, shows that it's probably going to produce carbon dioxide. And so that's our answer. Now, what about the identification of gases? How do you identify gases? Well, if you're talking about hydrogen, the test is usually done by using a burning splint. And when you use hydrogen with a burning splint, you want to discover that the hydrogen actually produces a pop sound. So because you can't see the gas, just try to use any gas and then you want to identify what kind of a gas it is. If you see that it produces a pop sound, then just know that that is hydrogen. Now, for oxygen, usually test oxygen with a glowing splint. And when you test this, you will discover that oxygen actually relights this glowing splint. So that's the difference between oxygen and hydrogen. Hydrogen produces a pop sound, oxygen relights a glowing splint. Now for carbon dioxide, usually you use lime water. So you test it with lime water, and what's going to happen is that it turns this lime water milky. So as you can see, you can easily distinguish between these three gases. Now for chlorine, usually you use or you test it with moist blue litmus. So you use moist blue litmus. And what's going to happen is that this chlorine is going to turn this litmus red and then bleaches it. So it's going to bleach the litmus paper after turning it red. So that's chlorine. Now the other gas that we can talk about is actually sulfur dioxide. Now for sulfur dioxide, for the most part we use acidified potassium dichromate. So you use acidified potassium dichromate. And what happens is that when you use acidified potassium dichromate to test for sulfur dioxide, what happens is that it turns it from orange to green. So when you see acidified potassium dichromate change to green from orange, then just know that what you are testing for is sulfur dioxide. Now, what are some of the uses of acids? What would you say? Well, hydrochloric acid is used to remove rust, and sometimes it is used to clean some metals. But when you're talking about sulfuric acid, this is the common acid that is in batteries. And sometimes it is used also in fertilizers. And the same is true for nitric acid, because it is also used in fertilizers, but also in explosives. For bases, you have, let's say, sodium hydroxide, and this sodium hydroxide is actually used in soap making. So when you're making soap, for the most part, you can use sodium hydroxide, and sometimes it can also be used in cleaning. When you're trying to treat water, sometimes you can use calcium hydroxide. So it is used in water treatment. And ammonia is something that you can use also in fertilizers, but also in cleaning. So make sure that you go through these concepts, because they are going to help you know how to answer different problems on acids, bases, and salts. So that's it for this video. Thanks for watching.